Okay, this is going to be a quicker video. So I'm just going to review these 5 problems. And what I am going over, even though it says assignment up here, is not your assignment. You're not going to do this. You are going to do a 10-question quiz. It doesn't count as a quiz. It's just going to count as an assignment. You do your best. You get the 10 out of 10 for doing it. But it's just a brief review of what we did just before break. So I'm gonna review the concepts, and then you're going to take the little 10-question quiz to kind of get the ideas going back in your mind. And then tomorrow, or the day after, tomorrow we'll pick up with new information. So let's talk about these graphs. We're going to do more than just sketch them because you're going to have questions, and I'll talk about that. So this is an exponential function because the variable is part of the exponent. There are 2 types. There are growth and decay. When you have a fractional base, this creates what we call a decay function. So that's going to be really important. You're going to need to know that. On the other hand, if the base is a whole number, it's going to be growth. Now I know you see this 1/2 right there, and you're saying that's not a whole number, but it's also not the base. It's not the thing that the power is attached to. So you don't need to worry about that. Just the base of the exponent is what matters. So back to this one. A fractional base means it is a decay function. If you are asked about an asymptote, the number that is added or subtracted is the horizontal asymptote. Always. So whatever number is added or subtracted, that's the horizontal asymptote. And if there is no number added or subtracted, then the horizontal asymptote would be the x-axis, or 0. But anyway, that is the horizontal asymptote. When you go to graph it, you could actually sketch that in before you do anything else. A horizontal line at +1. Now, let me change colors here. This number, the one that is either added to or subtracted from x, is the horizontal shift. This number is a horizontal shift. That means the graph moves to the left or to the right. A -2 specifically moves this graph right 2. Now you might see the minus and think that minus is in the left direction, so therefore it should be left 2. It actually works just the opposite of that, and we covered that earlier in the year when we went over parent functions and graphing. So the number that's added or subtracted to the x is the horizontal shift, and the direction is just the opposite of that sign. Now, if we were graphing by hand, I would really get into how to deal with that. But we're not going to be graphing by hand. We're going to be using the calculator. So you just need to know how to classify the shift in words: horizontal, left, right, and then the number. Now when it comes to graphing, you can just type this into your Desmos. So y equals 1 divided by 4. Oops. Okay, you got to get rid of that. And then times. Now here I'm going to use parentheses, 1 divided by 7, and then outside of the parentheses hit the power button. Use parentheses again for x minus 2, and then after that, +1. And then this is the graph we get. Let me move it a little bit. You see a y-intercept seems to be up there at 13.25, so right around here. As you can see, the horizontal asymptote is at +1, so I drew that horizontal line at +1. That's where the graph sort of levels off. So my graph is going to sort of be level with the horizontal asymptote, and then it's going to curve upward, and it goes like that. Now I drew it, well, that's pretty sloppy, but hopefully you can deal with that. I drew it in this direction. That's actually not quite right. Graphs always need to be read from left to right. And the reason I say this is, like, let's say you're a little car on this and you're moving from left to right. You're going to be going downhill. That's why we call it a decay, because it goes downhill from left to right. So since there's only 2 options, growth or decay, it's kind of expected that you'll know the difference. So when we do number 2, being a growth, it should be sort of like this. Now that's too vague. We're going to get specific, but let's answer all the questions. First of all, the horizontal asymptote right here, horizontal asymptote, is -2, so I could draw a little dotted line down here. This number again tells me that it's a growth because it's a whole number. +2 with the x means that this is going to move left 2 units. Doesn't really affect our graph the way we're doing it. If we're doing step by step how to graph by hand, I'd get more specific into that, but let's not worry about that. But you need to be able to classify it as a growth or a decay. You need to be able to identify the horizontal asymptote, and you need to be able to at least put into words the horizontal shift, whether it's left or right and how much. Now to actually graph it, y equals 1 divided by 2 times 3 raised to the, now here I'm going to use parentheses, x plus 2 power, and then go over, type -2. I'll hit the home button, and there we have, okay, 2.5 is the y-intercept. Looks like an x-intercept just short of -1. You can see the horizontal asymptote is down here at -2. There it is, -2. It sort of levels off. So I'm going to just draw a line that sort of levels off here, and then it makes a curve, and then it goes upward, and then it curves upward to infinity. And again, if you were a little car, here, this is the stupidest drawing of a car, but you're a little car and you're traveling left to right, which is always the way you read graphs, then this is going uphill. That's why we call it a growth. It's getting higher and higher. Ironically, because we're going through what we're going through with the coronavirus and all, in its early stages, viruses, they have a horizontal asymptote of 0. So we start with at least one of the viruses, and then it stays a low population for quite a while, but then as it starts to spread, it really takes off and it exponentially grows higher and higher and higher. Now, the virus will not go to infinity. It's actually not technically an exponential graph. It looks exponential for a while, but then it sort of levels off and you get this thing. It's kind of like a bell curve. It's called a bell curve because, well, I can't draw, but it's supposed to look like a bell with a handle, and oh wow, that's awful. Okay, I might just delete this video, probably not. But anyway, this actually kind of ties in with what we're going through right now. Kind of weird that it does, but in the short term, in exponential growth of a population of people in a city, growth of population of a species of rabbits in the wild, or growth of bacteria or viruses is exponential, at least for a while. Sometimes under controlled circumstances, they level off, they reach sort of a peak capacity, and then there's a second horizontal asymptote. That's called a logistic graph, if you really care. So they can't really go to infinity. Even in nature, there's got to be some upper limit. But what we're looking at is, again, something that sort of curves. That's why they talk about flatten the curve. So anyway, this does relate, at least, in a narrow aspect, as, what we're going through right now. So whether that's interesting or depressing, I'll leave that up to you. But let's move on. So now we're looking at solving exponential equations. There's the easy ones and then the ones that take a little more work. The easy ones are where the bases match, and you're just allowed to just cross those out. You get 2 minus 2b equals 2 left over. And then you solve that using your basic algebra skills that you've been using like what seems like forever now. And here we get b equals 0 is the solution to this one. Let's see, that b looks like a 6, so let's make it more like a b. Now, the trickier ones are where the bases don't match, and you can't just cross them off, so you have to make them match. And so like in number 4, seeing how these end both in 5, that kind of is a little tip-off that we can turn both of these bases into 5s. Now, how exactly do you do that? You might have some solid mental math skills, and that's great. Or you might need to grab a calculator. So I'm going to do 5 times 5, and that's 25, times 5, 125, which is what we've got here. So it took 3 5s to do that. That means we've got 5 to the 3rd power. But that still has this power attached to it. So I got to bring that down. Now over here on the other side is 625. So 5 times 5 times 5, you can see is still on the calculator. If I go times 5 again, now it says 625. So that's 5 to the 4th power. So what we did is we kind of creatively turned both of these bases, oops, that's not what I wanted, both of these bases into 5s. Now that they match, you cross them out. Over here on the left, you can actually distribute this and you get negative 9r plus 9. Over on the right, you just have that 4. I'm going to subtract 9 on both sides. Negative 9r equals negative, 5, 4, excuse me, 4 minus 9, negative 5. Then divide by negative 9. Of course, you can't divide 5 by 9, but the negatives cancel and you get 5/9. So, and you get fractions as answers. Sometimes it just happens. Number 5, again, is another one where we have to make the bases match. And 27 and 81 might be sort of foreign numbers to you, but I'll give you, I'll just kind of tell you how it works. They're both based on the number 3. So 3 times 3 times 3, you can see there is 27. So I can make this 1 over 3 to the 3rd, and that's to the negative 2p. On the other side, 81, well, if I hit times 3 again, there's 81. So that's 3 to the 4th, and that's to the 3p power. Now, this is really important. I cannot cross those out yet because on the left we have a base 3. On the right, we actually have a base 1/3, which is close to 3, similar to 3, but it's not a 3. So there's something called the negative exponent rule, which tells me that 1 over 3 to the 3rd can be rewritten as 3 to the negative 3rd. So when you need to reciprocate a fraction, you just make the power negative. And there is one of these on the little quiz you're going to take. I think it's 1 over 64 or 1 over 4, something like that. So remember, if you've got a fraction, but you want to turn it into a whole number, go ahead and turn it into a whole number. Just make its power negative, and then it all magically works out. So the bases cancel. Over here, I get 12p. Over here, I get 6p. Ooh, that's interesting. Then I get my like terms together. I get 6p equals 0. When you divide by 6, p equals 0 is the answer. So 3 and 5 were both 0, is that right? Yeah. Did not plan that. Don't expect to see zeros come up often. I think it's just a weird coincidence that it happened here. But anyway, those are the concepts. So I did 5 examples. You're going to actually have 10 questions. These graphing questions are going to be broken down into individual pieces instead of handling the whole idea all at one time. So this video should explain everything. Watch it more than once if you need to. When you go to do the quiz, shoot for a perfect 10 out of 10. It'll grade it for you when you do it. You don't have to get a perfect 10 out of 10. It would be great to see some of you, if you score low, to retry. I get a little spreadsheet with the results. So if I see you got like a 5 out of 10 the first time and then you got a 9 out of 10 the second time, even if you didn't have to do it, it's nice to see that you're putting in the effort and you're making an improvement. So go ahead and do that. You have to do the spreadsheet. Don't forget to fill in the attendance as well, and look for new material starting tomorrow. All right, take care.